In this video, we'll take a look at some electrical characteristics we need to consider when we're implementing our binary logic. We'll start out looking at positive and negative logic, and that associates voltage levels, or sometimes called signal levels. That's the voltage level of the signal. It associates those levels with the two possible binary logic values of 0 or 1. So positive logic is what we have been discussing, where a logic value of 0 is associated with a low voltage level. We saw that on the oscilloscope. The voltage near 0 was a logic level 0 we considered, and a voltage low. A logic level of 1 is a high value. So what is low or high depends on the implementation. But obviously low tends to be 0 volts for our DC circuits. If we have negative logic, then a logic level of 1 is associated with the low signal value, and a logic level of 0 is associated with the high logic value. So the IC specifications, that we've seen, identify the truth table in terms of the signal value, the voltage level of low or high, not with the logic value, because they're concerned with the electrical, not the logic design. So if we look at an example of our dual functions, a positive logic AND is the equal of a negative logic OR. So if our electrical specification is such that we have our our logic levels for X and Y at the inputs of our digital gate, and our logic levels for our output of the logic gate, here in the truth table we show F, in this block diagram we show Z, they should match. So what I'm going to do here is, just so that they match, we'll change that to a Z, and that matches our digital gate. So if that's what it's defined, and we're using positive logic, then we can substitute in where we have a L, a logic level 0, where we have an H, a logic level 1, and we can see what we have is the truth table for an AND gate. So that would give us this gate symbol for a positive logic AND. If we were using negative logic, we'd substitute a logic level 1 for a voltage level L or low, and a binary logic 0 for a voltage level high. And we see here what we end up with is a OR gate, right? It's in the reverse order, 0, 1, 2, 3 from bottom to up, but this is an OR gate. So this is a negative logic OR gate, and what we use to show that it's negative logic is these little triangles at each of the inputs and at each of the outputs. Now that's different from our bubble, right? Our bubble, that's a NOR gate, and that's a positive logic NOR. Logic NOR gate. So we want to differentiate between the electrical specification and the binary logic values. If, for example, we want to implement this, which is a NOR gate, right? This is an OR gate. If it was positive logic, what would that specification look like? Where we have a 0, we'll put in L's. Where we have a 1, we put in H's, HL, HH, and then we have L, H, H, H. And that's what we might expect. If it's negative logic, however, where we have a 0, we put it in an H, and where we have a 1, we put in an L, so we have an L, H, L, L, and then L, 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 H. So there's our negative logic OR gate. So make sure you can differentiate between the two. That's our positive and negative logic levels. So let's also look at different levels of integration. We'll start out working with NANDs and NORs and 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 ORs, and those are small scale integration on the order of 10 gates or 10 transistors within the IC itself. Medium scale integration on the order of 10 to thousands of gates, that's like the counter that we worked with, the 7493. Also we'll work with other digital functions, decoders, multiplexers, and adders. If we want large scale integrations, thousands of gates, it's memory chips, small microprocessors, and EPROMs, and we'll talk about some of those later in the semester. At very large scale integration are VLSI and VVLSI, where we get hundreds of thousands of gates. So again, what do we mean by a gate? That's our digital switch, or electronic switch, I should call it, and that's primarily what we use in digital logic is the CMOS. This is what we started out looking at, and how we could show we can control the gate, whether it conducts or it does not conduct, depending upon, this shows the logic value at the input of the gate, where what we're really talking about is the voltage level at the input of the gate, whether we have a PMOS or an NMOS transistor. We know, of course, we're reminded of Moore's law, that our IC capacity doubles every 18 months. That's been happening for decades. We have billions of ICs and billions of transistors on a single IC to create our processors. So we also have to consider the logic family, where we use resistor transistor logic and diode transistor logic. Those are the original transistors. Transistor logic is the oldest standard, TTL, and that's a standard we've been using primarily in lab. Emitter coupled logic is much higher speed and has that advantage electronically. So higher speed means we can run things at higher frequencies. Higher frequencies make a big difference when we're using our computers. The MOS has a much higher MOS level, metal oxide semiconductors, much higher component density. So that was a big deal for being able to fit more ICs in more transistors on one IC. The complementary metal oxide semiconductors use lower power, so that's what was primarily used in our very large scale integration. Additionally, there are logic families that use 3 volts and 2 volts, so we can even lower the power. We won't be using those in lab. So basic characteristics we want to be aware of for our logic families are the fan out, the fan in, the power dissipation, the propagation delay, and the noise margin. We've talked to some degree about the noise margin and what's considered a valid input high, a valid input low, what's considered an acceptable output driven high, what's considered an output driven low for the different TTL or CMOS families. What we'll talk about additionally is fan out, how many loads an output can drive, fan in, the number of inputs a gate has, the power dissipated by the gate, and the propagation delay through the gate. That's important for us electronically in the lab, and we'll be exploring propagation delay in the lab. So let's look at fan in, the number of inputs a gate has. So a 2-input AND gate has a fan in of 2. A 3-input NAND gate, for example, has a fan in of 3. Our NOT gate or inverter always has a fan in of 1. That just has 1 input and 1 output. So the number of inputs is the fan in. If we increase the number of inputs, this shows our gate delay versus fan in, and we see how that in fact increases. So if we have a 2-input NAND gate, that's going to have, in this example, a propagation delay on the order of just 100 picoseconds, whereas a 4-input NAND gate has a propagation delay about twice that at 200 picoseconds. Fan out considers how many loads an output can drive. So if you're going to have an output of a NAND gate, how many other devices can you have that go into? So what can happen is if your load is too high, then it can't actually source or sink the right amount of current. It's sourcing current when it's trying to drive the signal high, it's sinking current when it's trying to drive the signal low. And if we have too much load there, then the low state may increase above the maximum acceptable value for an output low. For example, at TTL, you must pull that output low down to, I think, 0.4 volts. You must pull that output high up into about 2.4 volts, so you might not be able to do that. Additionally, the temperature of the device will increase, so that reduces the reliability and you have eventual failure of the device. So that would happen over long term. After the device has been used for a while, you wouldn't necessarily experience that in lab. But you could experience output rise and fall times increasing beyond spec, and the propagation delay increasing. Again, that propagation delay increasing is going to affect how fast you can run your circuit, or the frequency at which you can run your circuit. This shows a gate delay versus fan out, so of an inverter and of a NAND gate. So an inverter has less propagation delay than a NAND gate. There's less transistors there. And it looks, again, approximately linear. As you increase your load, approximately linearly, you increase the delay through the gate. So what do we mean by that propagation delay? That gate delay is the delay from our input X. If we look here at this inverter signal, at the input is X, at the output is X prime, or X inverted. When X transitions from high to low at the input, the amount of time it takes for the output to then transition from low to high, that's your propagation delay. What you additionally have to be aware of is the delay for a signal to go from low to high is not always equal to the delay for a signal to go from high to low. So there's two different propagation delays specified for an IC, or for a gate. Additionally, we could have transport delay along the wire, which has to be considered. So the total delay, for example, for X to transition, it goes through an inverter, then through along a wire, the signal travels along a wire, and then goes through another inverter and becomes Y prime. So the total delay before X goes from high to low until our X goes from low to high until Y goes from low to high includes the propagation of the propagation delay through this gate and the wire delay, transport wire delay. All right, so let's look at that definition of propagation delay, and this is again what we'll use in the lab. So we consider that propagation delay is measured at the midpoint. So if we have a signal rising from 0 volts to 4 volts, when this input gets to 2 volts, that's when we start to calculate our delay from. So we have our input going through, and it looks like from input to output we have a signal being inverted. So when the input transitions from 0 to 2 volts, we look for the output. If this is originally also at 4 volts, when it gets down to 2 volts, that's going to be our propagation delay from high to low. So our specification, T for time, subscript P, propagation delay, high, low, and that's different from TPL, high. And again, where we're measuring those from is at the midpoints. Again, a rise time is the time required for the output voltage to increase from our input low maximum to our input high minimum. Fall time, the time required for the output voltage to decrease from input high minimum to input low maximum. Remember, these specifications are different for the different technologies, TTL or CMOS technologies, but the input is what the circuit is going to be considered low at its maximum input, and it's going to be considered high at its minimum input. That's if it's going from low to high, and reverse is from going from high to low. So we'll review here our different technologies, TTL or CMOS. If we look here, in our noise margin, we have a much larger noise margin here at the output voltage than we do at the input side. If we compare this, TTL has an output high of 2.4 volts and an input high. It only needs 2 volts, then that input's going to be considered high. CMOS needs to drive the output high to 4.9 volts, but it'll read a 3.5 as our input high. And again, our TTL must drive its output down to 0.4 volts, but we'll consider 0.8 volts at the input as a low level. So we can also compare their noise margin. So our low state noise margin for TTL is 0.4 volts. Our noise margin for CMOS is 1.4 volts for the low noise margin. The high noise margin, again, 0.4 volts for CMOS, and the 1.4 volts for 1.4 volts for CMOS and 0.4 volts for TTL. So let's take a look at a NAND circuit. If we take a look at a NAND circuit, we can find our output high, our output low, And I guess that's all we have in here. We don't have the input high, input low. So it shows for what we're pulling it up to for power. It's looking at 4.5 volts and 5.5 volts, the range that we can pull up for power. We have minimum, typical, and maximum ranges. So our output high, and so it considers the current here. If we look SN74, this is ACT, so this is our CMOS device. It requires that the output high is driven to a minimum of 4.4 volts when the VCC is 4.5 and 5.4 volts when the VCC is 5.5. Again, that's your minimum. Maximum doesn't need to be specified here, and then you can look for your output low showing the 0.1. If this was TTL, you could tell whether it's CMOS or TTL based on these levels here. On our standard TTL, again, our minimum, maximum voltage conditions, and then the current that must be required. Okay, so that's it for this video. This is what we'll work with in lab.